Gravity is everywhere. It keeps us grounded, guides our movements, and quietly shapes the world around us. Because it is so familiar, we rarely stop to question it. Yet, this gentle force governs the most powerful events in the universe, from collapsing stars to the motion of entire galaxies. Strangely, in the language of physics, gravity is also the weakest of all fundamental forces. How can something so subtle hold such immense power? Tonight, we begin a journey to explore gravity's true nature, and the mystery of why this quiet force plays such an extraordinary role in the cosmos. For most of its life, a star exists in a delicate and almost peaceful balance. At its core, immense pressure and temperature force atomic nuclei together, fusing hydrogen into helium and releasing vast amounts of energy in the process. This energy pushes outward, creating a constant pressure that resists collapse. At the same time, the star's enormous mass pulls inward under its own gravity. As long as these two influences remain in balance, the star shines steadily. Gravity pulls in, nuclear fusion pushes out. For millions, sometimes billions of years, this quiet struggle continues, but no star wins forever. Eventually, the fuel that powers fusion in the core begins to run out. Hydrogen becomes scarce. Fusion slows. And when that outward pressure weakens, gravity, patient and relentless, finally gains the upper hand. What happens next depends on the mass of the star. For smaller stars, like our Sun, the ending is relatively gentle. The outer layers drift away, forming glowing planetary nebulae, while the core settles into a dense white dwarf. Gravity tightens its grip, but not violently enough to tear the star apart. For massive stars, however, the story is far more dramatic. As fusion slows in the core of a large star, gravity accelerates the collapse inward. The core contracts rapidly, compressing matter to densities almost beyond comprehension. Temperatures soar, and the internal structure of the star begins to fail. Electrons, which normally resist being squeezed together thanks to quantum mechanical effects, can no longer hold back the crushing force of gravity. In a fraction of a second, the core collapses at speeds approaching a quarter of the speed of light. This sudden implosion sends shock waves racing outward. The result is a supernova. In that brief and violent moment, the star releases an extraordinary amount of energy. The outer layers are blasted into space, carrying newly forged elements across vast distances. These elements, carbon, oxygen, iron, and many others, will eventually become part of future stars, planets, and even living organisms. Supernovae are among the most luminous events in the universe. For a short time, a single exploding star can outshine the entire galaxy that hosts it. The blast wave expands for years, carving through the surrounding interstellar medium and reshaping the local cosmic environment. And yet, as powerful as a supernova may appear, it is not the most extreme expression of gravity's influence. In rare cases, the universe goes even further. When a star is more than 30 times the mass of our Sun, gravity's victory is not just decisive, it is overwhelming. As fusion fails, the collapse does not stop at the formation of a neutron star. Instead, the core continues inward, crossing a threshold from which there is no return. A black hole is born. As the core collapses, it drags surrounding material with it, twisting space and time into a deep gravitational well. Matter spirals inward, heating to incredible temperatures. Magnetic fields intensify. Jets of radiation and high-energy particles are launched at near-light speed, piercing through what remains of the star. This process ignites a hypernova. Hypernovae are not simply stronger supernovae. They are fundamentally more extreme. Their energy output can exceed that of a typical supernova by a factor of 10, or even 100. The light they produce can travel across billions of light years, briefly announcing the death of a star to the farthest reaches of the observable universe. In these events, gravity does more than cause collapse. It organizes chaos. The inward pull concentrates matter. The rapid rotation focuses energy into narrow beams. The warping of space-time itself guides the flow of radiation and particles outward in violent, focused bursts. Gravity is not merely a background force here. It is the architect of destruction. What makes this especially striking is the scale at which gravity must operate to achieve such results. On Earth, gravity feels gentle. We overcome it every time we stand, jump, or lift an object from the ground. Compared to the other fundamental forces, gravity appears almost insignificant. And yet, when enough mass is gathered together, when entire stars and stellar cores are involved, gravity becomes unstoppable. It does not need to be strong in the conventional sense. It only needs time and mass. Given enough of both, gravity can compress matter until atoms themselves collapse, forge new elements in moments of catastrophic violence, and leave behind objects so dense that even light cannot escape their pull. From supernovae to hypernovae, from neutron stars to black holes, the most dramatic events in the cosmos are all, at their core, expressions of gravity finally winning a long and patient battle. And this is where the paradox begins to take shape. If gravity is capable of driving explosions that outshine galaxies and reshape the universe, why does it feel so weak in our everyday lives? Why is it the faintest of the fundamental forces, despite being responsible for the most extreme phenomena we know? To answer that question, we must step away from dying stars and look more closely at gravity itself, not as a cosmic destroyer, but as a fundamental interaction among many others. That journey begins with a comparison. Gravity is so deeply woven into our everyday experience that it almost disappears from our awareness. From the moment we learn to stand upright, our bodies adapt instinctively to its pull, adjusting balance and movement without conscious thought. We walk, sit, lift objects, and fall asleep each night with gravity quietly shaping every motion. It becomes so familiar that we rarely stop to question its nature or its strength. Gravity feels less like a force and more like a background condition of existence itself. Throughout our lives, we unconsciously calculate gravity's effects. When we throw a ball, we adjust for its downward arc without ever thinking about equations or forces. Athletes refine their movements around gravity, learning how high they can jump and how far they can throw. Even simple activities like climbing stairs or carrying groceries are constant negotiations with gravity's pull. On the scale of daily life, gravity feels dominant, unavoidable, and ever-present. Nowhere is this dominance more apparent than in humanity's attempts to leave Earth. Rockets do not merely need to move forward or upward. They must fight against the gravitational pull of an entire planet. Engineers design massive engines, complex fuel systems, and multi-stage rockets primarily to overcome gravity long enough to reach orbit. The challenge of spaceflight makes gravity feel like a formidable opponent, one that demands enormous energy and precision to defeat. From this perspective, gravity seems anything but weak. And yet, when physicists step back and examine gravity at the most fundamental level, a very different picture emerges. In the language of modern physics, gravity is not the central force it appears to be in everyday life. Instead, it is classified as just one member of a small group known as the fundamental forces of nature. These forces are the basic interactions from which all physical phenomena arise, governing everything from subatomic particles to the largest structures in the universe. There are 4 such forces known to physics today, and each plays a distinct role in shaping reality. The first is the strong nuclear force, the most powerful of all. It binds quarks together to form protons and neutrons and holds those particles tightly within atomic nuclei. Without the strong force, atoms would instantly fall apart, and matter itself could not exist in any recognizable form. Next comes the electromagnetic force, which governs electricity, magnetism, light, and chemistry. It is responsible for the attraction and repulsion between charged particles and allows atoms to bond into molecules. Every chemical reaction, every electrical signal in the brain, and every beam of light traveling through space is a manifestation of electromagnetism. On human scales, this force is far stronger than gravity, even if we do not always notice it. The third fundamental interaction is the weak nuclear force. Despite its name, the weak force plays a crucial role in the universe. It governs radioactive decay and is responsible for the nuclear reactions that power stars, including the fusion processes that make the sun shine. Without the weak force, the universe would be dark, cold, and lifeless, incapable of sustaining stars or complex matter. And finally, there is gravity. Unlike the other forces, gravity acts on all forms of energy, and mass might suggest that gravity should be the strongest of the fundamental forces. After all, it governs the motion of entire galaxies and drives the formation of stars and black holes. But when physicists compare the actual strengths of these forces at the level of fundamental particles, the result is deeply unsettling. Gravity does not merely come last in this comparison. It trails behind by an almost unimaginable margin. When measured between elementary particles, gravity is weaker than the electromagnetic force by many orders of magnitude. More striking still, it is weaker than even the weak nuclear force by a factor of around 10 to the 25th power. This means gravity is roughly 10 trillion times weaker than a force already considered feeble by comparison to the strong and electromagnetic interactions. The scale of this disparity is so vast that it defies everyday intuition. This extreme weakness has profound consequences. At the scale of atoms and particles, gravity is essentially irrelevant. It plays no role in holding atoms together, shaping chemical bonds, or influencing the behavior of subatomic particles. Those realms are governed entirely by the other three forces. Gravity only begins to matter when enormous quantities of mass are involved, when the tiny contributions from countless particles accumulate into something significant. A simple example makes this imbalance easier to grasp. Consider a small ant standing on the surface of the Earth. The planet beneath it has a mass of nearly 6 trillion kilograms, yet the ant can lift its legs and walk with ease. The chemical energy stored in the ant's muscles, governed by electromagnetic interactions, is more than enough to overcome the gravitational pull of the entire planet over short distances. This is not because the ant is strong, but because gravity is extraordinarily weak. The same principle applies to humans. Every time we stand up, climb stairs, or jump into the air, we momentarily overcome Earth's gravity. We do this using energy derived from chemical bonds, not from any exotic source of power. Gravity feels constant and inescapable because it acts continuously, not because it is particularly strong. Compared to the forces that govern matter at small scales, gravity is barely present at all. This creates a remarkable contradiction at the heart of physics. Gravity is responsible for the most violent and energetic events in the universe, from supernovae to black hole mergers. It shapes the largest structures ever observed and governs the evolution of the cosmos itself. Yet at the most fundamental level, it is astonishingly weak, easily overwhelmed by forces operating within atoms and molecules. The reason gravity can dominate the universe despite its weakness lies in its cumulative nature, unlike the other forces, which can cancel out through positive and negative charges or operate over limited ranges. Gravity always adds up. Mass attracts mass, without exception. and there is no such thing as negative mass to cancel its effects. Given enough matter and enough time, gravity's influence becomes overwhelming, even if each individual contribution is tiny. Still, this explanation only shifts the mystery rather than resolving it. It tells us how gravity manages to dominate on large scales, but it does not explain why gravity is so weak to begin with. There is no obvious reason, based on our current understanding of physics, why gravity should be separated from the other forces by such a vast gulf in strength. This imbalance appears unnatural, as if something fundamental is missing from the picture. Physicists have given this puzzle a name: the hierarchy problem. At its core, the hierarchy problem asks why gravity is so much weaker than the other fundamental forces. According to many theoretical expectations, gravity should be far stronger than it is observed to be. Calculations suggest it should be closer in strength to the other forces, not separated by 25 orders of magnitude. The fact that gravity is not stronger implies that something is suppressing it, diluting its effects in a way that current theories struggle to explain. This suppression cannot be dismissed as coincidence, because it has profound implications for the structure of the universe. If gravity were even slightly stronger, stars would burn differently, galaxies would form in other ways, and life as we know it might not exist at all. This realization transforms gravity's weakness from a curiosity into a clue. Rather than being an inconvenience or anomaly, gravity's feebleness may be telling us something deep about the nature of reality. It suggests that gravity might not be a force like the others, or that it might originate from a different layer of the universe altogether. Its behavior hints at a deeper structure waiting to be uncovered. To move forward, physicists must look beyond how gravity behaves and begin asking where it comes from. Answering that question means stepping back into the earliest moments of the universe and questioning assumptions about space, time, and even the number of dimensions that exist. The paradox of gravity does not end here. It opens the door to a far larger mystery. And it is that mystery, the origin of gravity itself, that now demands our attention. Once the paradox of gravity becomes clear, it is impossible to ignore the deeper question that follows. If gravity governs the largest structures in the universe, yet barely registers among the fundamental forces, then its weakness cannot be a coincidence. Nature rarely allows such extreme imbalances without reason. Somewhere beneath the equations and observations, there must be an explanation for why gravity behaves so differently from everything else we know. Gravity is everywhere. It reaches across interplanetary space, binds stars into galaxies, and shapes the evolution of the universe on the grandest scales imaginable. Unlike the other forces, it does not fade with distance in any meaningful way, and it acts on all forms of mass and energy without discrimination. Yet, when we zoom in to the smallest scales of reality, gravity all but disappears, drowned out by stronger interactions that dominate the microscopic world. This strange combination of universality and weakness makes gravity uniquely difficult to understand. For centuries, scientists were content to describe how gravity works without asking where it comes from. As long as its effects could be predicted accurately, its origin seemed almost secondary. But as physics advanced, and the gap between gravity and the other forces became impossible to ignore, that attitude began to change. The hierarchy problem did more than highlight a numerical imbalance. It exposed a conceptual gap in our understanding of nature itself. To ask where gravity comes from is to ask whether it truly belongs in the same category as the other fundamental forces. The strong, electromagnetic, and weak forces are all mediated by fields that fit comfortably within the framework of quantum mechanics. They operate through exchange particles, follow well-defined rules, and behave predictably at small scales. Gravity, by contrast, resists this framework, behaving smoothly and geometrically rather than discretely and quantized. This difference suggests that gravity may not be fundamental in the same way. One possibility is that gravity is deeply tied to the earliest moments of the universe. In its infancy, the cosmos was an environment unlike anything we can observe today. Temperatures were unimaginably high, densities were extreme, and the familiar distinctions between forces may not yet have existed. In such conditions, gravity might have emerged alongside space and time themselves, rather than as a force acting within them. If this is true, gravity's weakness today could be a relic of those early conditions, frozen into the structure of the universe as it expanded and cooled. Another possibility is even more radical. Gravity's weakness may be an illusion caused by our limited perspective. We experience the universe as having 3 dimensions of space and 1 of time. But this may not be the full story. If space has additional dimensions beyond those we can perceive, gravity could be spreading itself across a much larger arena than the other forces. In doing so, it would appear weak within our familiar dimensions, even if it is not fundamentally weak at all. These ideas may sound speculative, but they arise directly from attempts to reconcile gravity with the rest of physics. The deeper scientists dig into gravity's behavior, the more they are forced to question assumptions that once seemed unquestionable. Concepts like space, time, and dimensionality, once treated as fixed backdrops, begin to look more like dynamic participants in the story. Before exploring such radical possibilities, however, physicists first had to confront gravity as it was originally understood. To understand how far modern ideas depart from earlier thinking, we must return to the moment when gravity was first described in a systematic and mathematical way. That journey begins not in the depths of space, but in the quiet countryside of 17th century England. At the time, gravity was not viewed as a mystery of cosmic origin or extra dimensions. It was a practical problem, tied to falling objects, planetary motion, and the mechanics of everyday life. The challenge was not to explain why gravity existed, but to capture its behavior in a form precise enough to make reliable predictions. That task fell to one of the most influential figures in the history of science. Isaac Newton lived in a world where the heavens and the earth were still thought of as fundamentally different realms. Celestial objects followed divine or perfect paths, while earthly objects obeyed more mundane rules. Bridging this divide required a conceptual leap that few were prepared to make. Newton, driven by an intense focus and an almost obsessive dedication to his work, was uniquely positioned to take that leap. When Newton formulated his law of universal gravitation, he did something extraordinary. He proposed that the same force causing an apple to fall from a tree also governed the motion of the moon and the planets. Gravity, in his view, was universal, acting everywhere in the same way. This idea alone reshaped humanity's understanding of the cosmos, unifying the heavens and the earth under a single set of laws. Yet even as Newton's equations proved astonishingly successful, he remained deeply uneasy about what they implied. His law described how gravity behaves, but it offered no explanation for how one object could influence another across empty space. The notion of action at a distance troubled him profoundly, and he refused to accept it as a true explanation. In this sense, the question of gravity's origin was present from the very beginning, even if it was not yet clearly articulated. As long as Newton's theory continued to work, that discomfort could be set aside. For nearly 2 centuries, his equations predicted the motions of planets and moons with remarkable accuracy. Gravity, whatever its true nature, seemed mathematically well-behaved and practically reliable. But cracks eventually began to appear, and when they did, they forced scientists to reconsider not only Newton's theory, but the very foundations of gravity itself. Those cracks did not appear all at once. They emerged gradually, as observations became more precise and instruments more powerful. Small discrepancies accumulated, subtle deviations that Newton's equations could not fully explain. At first, these anomalies seemed like minor technical issues, but over time, they grew impossible to ignore. This slow accumulation of problems marked a turning point. Gravity could no longer be treated as a solved problem with an unexplained origin. Instead, it became clear that understanding gravity would require rethinking some of the most basic assumptions about space, time, and motion. The question of where gravity comes from could no longer be postponed. In this sense, gravity's weakness is not just a numerical curiosity, it is a signpost. It points toward a deeper layer of reality, one that lies beneath the familiar world of forces and particles. Whether that layer is hidden in the universe's earliest moments, embedded in extra dimensions, or woven into the geometry of space-time itself, remains an open question. What is clear is that gravity refuses to be understood in isolation. To uncover its origin, we must follow the path that physics itself has taken, from its earliest formulations to its most radical, modern ideas. That path begins with Newton, but it does not end with him. Instead, it leads through a series of revolutions that gradually reshape our understanding of reality. And so, to move forward, we must look back. We must revisit the first attempt to describe gravity, not to criticize it, but to understand its limitations. Only by seeing where the original picture falls short can we begin to glimpse what gravity truly is, and why it occupies such a strange and singular place in the universe. By the middle of the 17th century, humanity's understanding of the universe was still deeply fragmented. The heavens were thought to obey one set of rules, while the earth followed another. Planets moved in elegant paths across the sky, seemingly untouched by the messiness of everyday motion, while objects on earth fell, rolled, and collided in ways that felt fundamentally different. The idea that a single principle might govern both realms was far from obvious. Isaac Newton entered this intellectual landscape as a man of extraordinary focus and discipline. He was intensely private, deeply serious, and almost obsessively devoted to his work. Social distractions held little interest for him, and his life revolved almost entirely around study, experimentation, and calculation. This singular concentration, while isolating, allowed him to pursue questions with a depth and persistence few others could match. In 1666, an outbreak of plague forced Cambridge University to close its doors, sending Newton back to his family home in rural Lincolnshire. Removed from the academic world and living in relative isolation, he found himself with long stretches of uninterrupted time. What might have been a period of stagnation for others became one of the most productive phases of Newton's life. During this time, he worked on optics, mathematics, and the foundations of what would later become classical mechanics. It was during these months away from Cambridge that Newton began thinking deeply about motion and attraction. According to accounts that Newton himself later encouraged, he observed an apple fall from a tree while sitting in contemplation. Whether the story is literal or embellished matters less than the idea it represents. The falling apple prompted Newton to wonder why objects consistently accelerate toward the ground, and whether the same influence might extend far beyond the surface of the Earth. Rather than treating gravity as a local phenomenon tied only to our planet, Newton imagined it reaching outward into space. If the Earth could pull an apple downward, perhaps it could also pull the moon toward it, guiding its motion through the sky. This was a radical step, because it suggested that the same force acting on everyday objects was responsible for celestial motion. The boundary between Earth and heaven began to dissolve. From this line of reasoning emerged the law of universal gravitation. Newton proposed that every object in the universe attracts every other object with a force proportional to their masses and inversely proportional to the square of the distance between them. This simple mathematical relationship captured an astonishing range of phenomena. It explained why objects fall, why planets orbit the sun, and why moons remain bound to their planets. What made Newton's formulation so powerful was its predictive accuracy. Using his equations, Astronomers could calculate planetary positions with unprecedented precision. The motions of known planets fell neatly into place, and previously unexplained behaviors suddenly made sense. Gravity, once mysterious and qualitative, became something that could be calculated, predicted, and tested. For the scientific community, this was a triumph. Newton's law unified terrestrial and celestial mechanics under a single framework, offering a coherent picture of the universe governed by universal rules. For nearly 2 centuries, this framework reigned supreme. It became the foundation upon which classical physics was built, shaping everything from engineering to astronomy. And yet, Newton himself was never entirely satisfied. Despite the success of his equations, Newton was deeply troubled by what they implied. His law described how gravity behaved, but it did not explain what gravity was. In particular, the idea that one object could influence another across empty space, without any visible connection, struck him as profoundly unsettling. This concept of action at a distance felt to him like an admission of ignorance rather than an explanation. Newton openly expressed his discomfort with the notion that gravity was an innate property of matter. He resisted the idea that objects simply attracted one another without any mediating mechanism. To him, such a claim bordered on absurdity, especially for anyone engaged in serious philosophical inquiry. He believed that gravity must be caused by some agent acting according to fixed laws, even if the nature of that agent remained unknown. This hesitation reveals something important about Newton's mindset. He did not see his work as the final word on gravity, but as a step toward understanding its behavior. The mathematics worked, and the predictions matched observation, but the underlying cause remained elusive. Newton was willing to accept the limits of his explanation, even as others celebrated its success. For a long time, those limits did not seem to matter. Newtonian gravity worked extraordinarily well within the range of observations available at the time. The motions of planets, comets, and moons could be described with remarkable accuracy. Engineers and navigators relied on his equations with confidence. Gravity, though mysterious in origin, appeared stable and dependable. However, as observational tools improved, subtle discrepancies began to emerge. Small deviations in planetary orbits hinted that Newton's equations might not tell the whole story. These anomalies were not immediately alarming, but they planted seeds of doubt. If gravity were truly universal and complete, it should account for every observed motion without exception. One of the most troubling cases involved the orbit of Mercury. Careful measurements revealed that Mercury's path around the Sun did not behave exactly as Newton's theory predicted. The discrepancy was tiny, almost negligible, but persistent. Over time, it became clear that no adjustment within the Newtonian framework could fully account for the observed behavior. Another issue lay with light itself. According to Newton's laws, gravity acted on mass, but light appeared to have no mass at all. And yet, observations suggested that light could be influenced by gravity, bending as it passed near massive objects. This phenomenon could not be reconciled cleanly with Newton's conception of gravitational attraction. These problems did not immediately overthrow Newtonian gravity, but they exposed its limitations. The theory worked extraordinarily well in many contexts, but it was not universally accurate. Gravity, once again, proved to be more subtle than it first appeared. The very force that Newton had unified so elegantly now resisted complete explanation. What is striking is that Newton himself anticipated this outcome. His refusal to speculate about gravity's true nature was not an oversight, but a recognition of the theory's boundaries. He understood that describing gravity's effects was not the same as explaining its origin. In this sense, the question posed in earlier acts, where gravity comes from, can be traced directly back to Newton's own doubts. Newton's legacy, then, is not merely a set of equations, but a way of framing the problem. He showed that gravity could be treated as a universal phenomenon, subject to mathematical description and empirical testing. At the same time, he left open the question of its underlying cause, acknowledging that deeper explanations lay beyond his reach. This tension between success and incompleteness would shape the next stages of physics. As long as Newton's theory continued to work within acceptable limits, the mystery of gravity's origin could remain in the background. But as anomalies accumulated and new observations challenged old assumptions, that mystery could no longer be ignored. For a long time, Newton's theory of gravity appeared unassailable. Its equations worked so well that generations of scientists came to view them not as approximations, but as fundamental truths about how the universe operated. Planets followed predictable paths, comets returned on schedule, and the heavens seemed to obey Newton's mathematics with unwavering loyalty. Gravity, though mysterious in origin, behaved with reassuring consistency. As observational techniques improved, however, scientists began to look more closely at the details of planetary motion. Small discrepancies that once fell within the margins of error became measurable, persistent, and impossible to dismiss. These were not dramatic failures, but subtle deviations, the kind that only appear when a theory is pushed to its limits. Newton's universe did not collapse overnight. It slowly began to show signs of strain. One of the earliest and most troubling problems emerged from the orbit of Mercury. Mercury travels closer to the Sun than any other planet, moving through a region of space dominated by intense gravitational influence. According to Newton's laws, its orbit should follow a precise and predictable pattern, repeating itself endlessly in the same way. But careful measurements revealed that this was not quite the case. Mercury's orbit was observed to slowly rotate over time, a motion known as the precession of its perihelion. Some amount of precession could be explained by gravitational interactions with other planets, and astronomers accounted for these effects with meticulous calculations. Yet even after all known influences were included, a small residual discrepancy remained. Mercury's orbit shifted slightly more than Newtonian gravity could explain. At first, this discrepancy was treated as a curiosity rather than a crisis. Scientists explored various possibilities to preserve Newton's framework, including the existence of an unseen planet closer to the Sun or subtle errors in observational data. For decades, these ideas were investigated, refined, and ultimately discarded. The anomaly stubbornly refused to disappear. What made Mercury's behavior so unsettling was not the size of the discrepancy, but its persistence. Newton's theory was supposed to be universal, applying equally well everywhere in the cosmos. If it failed in even one carefully measured case, that failure demanded explanation. Gravity, it seemed, was behaving in a way that Newton's equations could not fully capture. A second and equally profound problem concerned light itself. In Newton's picture, gravity acted en masse, pulling material objects toward one another through space. Light, however, presented a challenge. It had no measurable mass and moved at extraordinary speed, seemingly untouched by forces that governed ordinary matter. Within the Newtonian framework, there was no clear reason why gravity should affect light at all. And yet, observations hinted that it did. As light from distant stars passed near massive objects, such as the Sun, it appeared to deviate slightly from a straight path. This bending was subtle, far beyond the reach of early telescopes, but it posed a serious conceptual problem. If gravity could influence light, then it could not simply be a force acting between masses in the conventional sense. Something deeper was at work. Newton himself had speculated about the nature of light, at times treating it as a stream of particles. Even within this interpretation, the gravitational deflection of light remained difficult to reconcile with his theory. The predicted amount of bending did not match what emerging observations suggested, and the theoretical justification felt increasingly strained. These issues highlighted a broader tension within Newtonian gravity. The theory treated space and time as fixed, absolute stages upon which forces acted. Objects moved through this immutable backdrop, responding to forces that reached across empty space. Gravity, in this view, was an invisible tether connecting masses, exerting influence instantaneously, regardless of distance. As long as observations were limited, this picture was sufficient. But as astronomy advanced, the universe revealed behaviors that did not fit comfortably within such a rigid framework. The idea of instantaneous action at a distance became increasingly problematic, especially as physics elsewhere began to emphasize locality, causality, and finite speeds of interaction. The growing discomfort with Newton's gravity was not merely technical, it was conceptual. Scientists began to question whether gravity should be understood as a force at all. The anomalies in Mercury's orbit and the bending of light suggested that gravity might be tied to something more fundamental than a simple attraction between masses. Space and time themselves were starting to look suspicious. Importantly, these problems did not imply that Newton was wrong in a general sense. His equations remained extraordinarily accurate across a wide range of conditions, and they continue to be used today in many practical applications. But accuracy is not the same as completeness. Newtonian gravity was revealing itself as an approximation, one that worked remarkably well under most circumstances, but failed under extreme conditions. The situation was reminiscent of earlier revolutions in science, where long-standing theories proved successful within certain limits but inadequate beyond them. Classical mechanics itself would later face similar challenges at high speeds and small scales. In the case of gravity, the limits were being exposed by the most precise observations available, pushing the theory beyond its comfort zone. As the 19th century drew to a close, physicists found themselves in an uneasy position. Gravity worked too well to be discarded, yet not well enough to be considered final. The anomalies were too consistent to ignore and too small to dismiss as experimental error. Something fundamental was missing, and the existing framework offered no clear path forward. This growing sense of incompleteness forced scientists to reconsider their assumptions. If gravity was not simply a force acting within space and time, perhaps space and time themselves were involved in producing gravitational effects. Such an idea would have seemed radical in Newton's era, but the accumulating evidence was beginning to demand radical thinking. The failures of Newtonian gravity did not point immediately to a solution, but they narrowed the field of possibilities. Any new theory would have to reproduce Newton's successes while also explaining Mercury's orbit and the behavior of light near massive objects. It would need to account for gravity's universality without relying on instantaneous action at a distance. This was a tall order, and for many years, no satisfactory alternative emerged. Physicists continued refining Newton's equations, searching for corrections or extensions that might resolve the discrepancies, but each attempt fell short, addressing one problem only to create another. Gravity resisted all efforts to be patched or repaired. What was becoming clear was that gravity required not a modification, but a reimagining. The very concepts of force, motion, and interaction were under scrutiny. The anomalies were not flaws to be smoothed over. They were clues pointing toward a deeper structure beneath the familiar equations. By the early 20th century, the stage was set for a transformation. The cracks in Newton's universe had grown too large to ignore, and the need for a new perspective was undeniable. Gravity, once the model of predictability, had become the gateway to profound uncertainty. To resolve the failures of Newtonian gravity, physics would have to abandon some of its most deeply held assumptions, and that leap would soon be taken by a new generation of thinkers, willing to question the very fabric of reality. That leap begins with an idea that, at the time, seemed almost impossible to accept: that space and time are not fixed and absolute, but dynamic and responsive. From this realization would emerge a new understanding of gravity, one capable of explaining what Newton's theory could not. And it is to that revolutionary shift that the story now turns. By the early 20th century, physics stood at a crossroads. Newton's laws still worked remarkably well in most situations, yet the cracks exposed by precise astronomical observations could no longer be ignored. At the same time, a new and unsettling theory had begun to reshape the understanding of motion, space, and time themselves. Albert Einstein's special theory of relativity had shown that measurements of space and time depended on the observer, challenging the idea that they were fixed and absolute. The implications of this shift were profound, and some physicists began to wonder whether gravity itself might need to be reimagined within this new framework. Among those thinkers was a Finnish physicist named Gunnar Nordström. Unlike Newton or Einstein, Nordström is not a household name, yet his role in the story of gravity is quietly significant. He was deeply influenced by the emerging ideas of relativity and was among the first to seriously attempt to reconcile gravity with this new way of thinking. Where Newton had treated gravity as a force acting across space and time, Nordström began to suspect that space and time themselves might play a more active role. Nordström's starting point was the realization that Newtonian gravity was incompatible with special relativity. Newton's theory allowed gravitational effects to propagate instantaneously, violating the relativistic principle that no influence can travel faster than the speed of light. This alone suggested that gravity could not remain unchanged in a relativistic universe. If space and time were interconnected and relative, then gravity would need to be reformulated in a way that respected those constraints. Rather than treating gravity as a force, Nordström explored the idea that it could be described through changes in the structure of space and time. His approach was mathematically elegant and internally consistent, building directly on the foundations laid by special relativity. In Nordström's theory, gravity altered the way clocks ticked and rulers measured distances, subtly reshaping the geometry of the universe. Objects moved not because they were pulled by a force, but because the geometry around them had changed. This was a radical departure from Newton's picture. Space and time were no longer passive stages on which gravity acted. They became participants in the phenomenon itself. Motion under gravity was reinterpreted as motion through a modified spacetime, where the straightest possible paths no longer appeared straight when viewed from within that geometry. The idea was difficult to grasp, even for physicists accustomed to abstract reasoning. What made Nordström's theory particularly intriguing was that it successfully reproduced many of the known results of Newtonian gravity. Planetary motions could still be described accurately, and the familiar predictions of Newton's equations emerged naturally in appropriate limits. From a purely mathematical standpoint, the theory worked. It respected the principles of relativity while preserving much of what had made Newton's gravity so successful. For a brief moment, it seemed possible that gravity had finally found a home within the relativistic universe. Nordström's work demonstrated that gravity could be described without resorting to action at a distance, and without violating the finite speed of causal influences. In doing so, it addressed some of the deepest conceptual problems that had plagued Newtonian gravity for centuries. However, physics is not governed by elegance alone. The ultimate test of any theory lies in its agreement with observation. As new experiments and measurements became possible, Nordström's theory faced challenges that it could not overcome. The most decisive test came from the behavior of light in a gravitational field. One of the key predictions of Einstein's special relativity was that light always travels at the same speed, regardless of the motion of the observer. This raised a critical question for any theory of gravity compatible with relativity. How does gravity affect light? Newtonian gravity offered no clear answer, and Nordström's theory provided a specific prediction that could, in principle, to be tested. According to Nordström's formulation, Gravity affected the passage of time, but did not curve space itself. As a result, light passing near a massive object would experience only a limited degree of deflection. This bending was significantly smaller than what would later be predicted by Einstein's theory. At the time, the difference between these predictions seemed subtle, but it would soon become decisive. The opportunity to test these ideas arrived with a total solar eclipse in 1919. During an eclipse, the sun's bright disk is obscured, allowing astronomers to observe stars whose light passes close to the sun on its way to Earth. If gravity bends light, the apparent positions of these stars should shift slightly during the eclipse. Measuring this shift would provide a direct test of competing theories of gravity. When the results of the eclipse observations were analyzed, they did not align with Nordstrom's predictions. The measured deflection of starlight was larger than his theory allowed, falling outside its acceptable range. In contrast, the results were consistent with a different theoretical framework that incorporated a more profound role for space-time geometry. Nordstrom's elegant construction, for all its mathematical appeal, was contradicted by nature itself. This outcome marked the end of Nordstrom's theory as a viable description of gravity. It could not account for all observed phenomena, and no minor adjustment could fix its shortcomings without undermining its core principles. From an empirical standpoint, the theory was effectively ruled out. Yet to view Nordstrom's work as a failure would be to miss its deeper significance. His theory represented the first serious attempt to move beyond Newton by embedding gravity within a relativistic understanding of space and time. He showed that gravity did not have to be a force acting at a distance, and that space-time itself could play an active role in gravitational phenomena. These ideas would prove essential for what came next. Nordstrom's influence extended beyond his equations. His willingness to rethink gravity at a fundamental level helped shift the mindset of the physics community. Concepts that once seemed unthinkable, such as non-flat spacetime, began to enter serious scientific discussion. The boundaries of acceptable theory expanded, making room for more radical ideas. Perhaps most telling is Nordstrom's relationship with Einstein. Rather than responding with resentment or rivalry, Nordstrom recognized the importance of Einstein's contributions and supported them openly. He even nominated Einstein for the Nobel Prize on more than one occasion, demonstrating a remarkable level of intellectual humility and integrity. In doing so, he acknowledged that the path to understanding gravity was a collective effort, not a personal contest. In hindsight, Nordstrom's theory can be seen as arriving too early. It contained the seeds of a revolutionary idea, but lacked the full conceptual framework needed to bring that idea to fruition. The notion that gravity might be connected to space-time geometry was present, but it had not yet been taken far enough. Space itself remained flat in Nordstrom's picture, limiting what the theory could explain. The failure of Nordstrom's approach clarified what any successful theory of gravity would require. It would need to explain not only the motion of massive objects, but also the behavior of light. It would have to reconcile gravity with relativity in a way that treated spacetime as dynamic rather than fixed. And it would need to produce testable predictions that matched observation with precision. These requirements narrowed the field of possibilities and sharpened the focus of physicists searching for a new theory. Gravity was no longer just a force to be modified or corrected. It was a phenomenon demanding a fundamentally new description. The shortcomings of Nordstrom's theory illuminated the path forward by showing where partial solutions fell short. In this sense, Nordstrom's contribution was indispensable. By demonstrating what could and could not work, he prepared the ground for a more complete theory. His ideas lingered in the background, influencing how others approached the problem of gravity's true nature. The notion of curved spacetime, once radical, began to feel inevitable. When Albert Einstein turned his attention to gravity, he did so with a deep sense of dissatisfaction. Newton's equations worked, but they relied on assumptions that no longer felt acceptable in a relativistic universe. Nordstrom had shown that gravity could not ignore relativity, but his solutions stopped short of explaining everything nature seemed to demand. Einstein suspected that the problem was not with gravity itself, but with the way space and time were being treated. If gravity refused to behave like a conventional force, perhaps it was never a force to begin with. Einstein's thinking was shaped by an unusual reliance on imagination rather than experimentation. He often referred to his ideas as thought experiments, simple mental scenarios designed to strip away unnecessary complexity and reveal underlying principles. One such experiment involved imagining a man falling freely from a great height. As the man falls, objects released from his hands remain suspended beside him, drifting as if gravity had vanished entirely. From the man's perspective, there is no gravitational field at all, only weightlessness. This simple scenario carried profound implications. If gravity could seemingly disappear for an observer in free fall, then gravity might not be an intrinsic force acting everywhere at all times. Instead, it appeared to depend on the observer's state of motion. What felt like gravity to someone standing on the ground vanished entirely for someone falling alongside it. This realization suggested that gravity and acceleration were deeply connected. Einstein extended this idea further with another thought experiment. Imagine a person enclosed inside a sealed box, floating freely in empty space, far from any stars or planets. Inside the box, the person would experience complete weightlessness. Now, imagine that the box is pulled upward with a constant acceleration by an invisible force. The person inside would feel pressed against the floor, experiencing a sensation indistinguishable from gravity. Without looking outside, there would be no experiment capable of revealing whether the box was accelerating or resting on the surface of a planet. This insight became known as the principle of equivalence, one of the cornerstones of Einstein's theory. It states that gravitational acceleration and acceleration caused by motion are locally indistinguishable. In other words, the effects we attribute to gravity may not be unique at all, but a consequence of how observers move through space and time. Gravity, in this view, begins to look less like a force and more like an aspect of motion itself. From this principle, Einstein drew a radical conclusion. If gravity and acceleration are equivalent, and acceleration is a matter of how objects move through space and time, then gravity must be connected to the structure of space and time themselves. Space and time could no longer be treated as rigid, passive backgrounds. They had to be dynamic, capable of responding to mass, energy, and motion. This marked a decisive break from Newtonian thinking. In Newton's universe, space and time were fixed and absolute, unaffected by what happened within them. Forces acted within this framework, but the framework itself remained unchanged. Einstein reversed this relationship, matter and energy. He proposed, determine the geometry of space and time, and that geometry, in turn, determines how matter and energy move. After years of intense mathematical struggle, Einstein presented his theory of general relativity in 1915. At its heart was a deceptively simple idea. Massive objects curve space-time, and objects moving through this curved space-time follow paths that appear to us as gravitational motion. Planets orbit stars not because they are pulled by a force, but because they are following the straightest possible paths through a curved geometric landscape. In this picture, gravity is no longer something that travels between objects. There is no invisible tether pulling masses together across empty space. Instead, mass and energy reshape the fabric of space-time itself, and motion unfolds naturally within that geometry. The Earth does not pull the Moon toward it. The Moon follows a curved path through space-time, shaped by the Earth's presence. One of the first major successes of general relativity was its explanation of Mercury's orbit. The small discrepancy that had troubled astronomers for decades fell naturally out of Einstein's equations. Mercury's close proximity to the Sun meant it moved through a region of space-time that was more strongly curved than Newtonian gravity accounted for. This additional curvature produced exactly the observed excess precession, without the need for hidden planets or arbitrary corrections. Equally striking was general relativity's prediction that light would be bent by gravity. In Einstein's theory, light follows the geometry of spacetime, just like any other entity, even though it has no mass. When light passes near a massive object, the curvature of spacetime alters its path, causing it to bend. This was not a side effect or an approximation. It was a direct consequence of spacetime geometry. The dramatic confirmation of this prediction came during the solar eclipse of 1919. Observations of starlight passing near the sun revealed a deflection precisely consistent with Einstein's calculations. The result captured global attention and catapulted Einstein to international fame. More importantly, it marked a turning point in physics, demonstrating that gravity was not a force in the traditional sense, but a geometric phenomenon. General relativity did not merely fix the problems of Newtonian gravity, it transformed the conceptual foundation of physics. Space and time became flexible, dynamic entities capable of stretching, compressing, and bending. Gravity emerged as a manifestation of this flexibility, linking geometry and motion in an inseparable way. The universe was no longer a static stage, but an active participant in its own evolution. Over the following decades, Einstein's theory was tested repeatedly and with increasing precision. It successfully predicted the behavior of clocks in gravitational fields, the bending of light by galaxies, and the existence of exotic objects such as black holes. Each confirmation strengthened confidence in the theory's accuracy and scope. Gravity, at last, had a description that matched observation across a vast range of conditions. Yet, for all its success, general relativity did not resolve every mystery. While it described how gravity works with extraordinary precision, it remained silent on a deeper question. The theory explained how space-time responds to mass and energy, but it did not explain why space-time should behave this way in the first place. The equations were elegant and powerful, but they did not reveal the origin of gravity itself. Einstein himself was acutely aware of this limitation. He recognized that general relativity was a classical theory, describing smooth, continuous space-time. It made no reference to the quantum nature of reality that governed particles and fields at the smallest scales. As physics progressed, this gap became increasingly troubling. Gravity stood alone, beautifully described yet fundamentally isolated from the rest of modern physics. This isolation hinted at a deeper problem. The other fundamental interactions fit naturally into the framework of quantum field theory, where forces arise from fields and are mediated by particles. Gravity, by contrast, resisted such treatment. Its geometric nature made it difficult to reconcile with the probabilistic, discrete world of quantum mechanics. The very feature that made general relativity so powerful also made it incompatible with other theories. As a result, general relativity came to be seen as both a triumph and a boundary. It represented the most complete classical description of gravity ever achieved, yet it marked the edge of our understanding rather than its culmination. Beyond it lay unanswered questions about the nature of space-time, the origin of gravity, and the structure of the universe at its most fundamental level. In this sense, Einstein's theory did not close the story of gravity, it deepened it. By redefining gravity as geometry, general relativity raised new questions that could not be answered within its own framework. Why should space-time curve at all? Why does gravity exist as a geometric property? And why is it so weak compared to other interactions? These questions could not be ignored indefinitely. As physicists pushed their theories toward more extreme conditions, such as the interiors of black holes and the earliest moments of the universe, the limitations of general relativity became increasingly apparent. The theory worked beautifully where space-time was smooth and well-behaved, but it struggled where curvature became extreme. The legacy of general relativity, then, is not just a new description of gravity. but a new way of thinking about reality. It taught physicists that forces might emerge from deeper structures, and that the geometry of the universe itself could be dynamic and responsive. At the same time, it left open the possibility that gravity is not fundamental, but emergent from something more basic. To move beyond Einstein, physicists would need new tools and new ideas. They would need to find ways to probe gravity in regimes where general relativity and quantum mechanics collide, and they would need new forms of evidence, capable of revealing aspects of space-time that cannot be seen through light alone. For decades after the publication of general relativity, gravity remained a theory confirmed largely through indirect observation. Planets followed predicted paths, light bent around massive objects, and time itself slowed in gravitational fields exactly as Einstein had described. Yet one of the most striking implications of the theory remained stubbornly out of reach. If gravity was truly a manifestation of curved space-time, then sudden, violent changes in mass and energy should send ripples through that fabric, propagating outward like waves on the surface of a pond. These ripples became known as gravitational waves. Einstein himself was unsure whether such waves could ever be detected. According to his equations, gravitational waves would be extraordinarily weak by the time they reached Earth, stretched thin by the vast distances of space, unlike electromagnetic waves, which interact strongly with matter. Gravitational waves pass through almost everything without resistance. They do not heat, ionize, or illuminate. Their integral challenges appeared overwhelming. Detecting gravitational waves would require measuring changes in distance far smaller than anything previously achieved in experimental science. Despite these doubts, a small group of physicists remained convinced that gravitational waves were not only real, but essential. If detected, they would provide direct evidence that gravity behaves as Einstein predicted, propagating at a finite speed rather than acting instantaneously across space. More importantly, they would offer a new way of observing the universe, one that did not rely on light at all. This ambition gave rise to an extraordinary experiment, the Laser Interferometer Gravitational Wave Observatory, known as LIGO. Rather than attempting to observe distant cosmic events directly, LIGO was designed to detect the tiny distortions in space-time caused by passing gravitational waves. It consisted of two massive interferometers, one in Hanford, Washington, and the other in Livingston, Louisiana, separated by thousands of kilometers to eliminate local interference. Each LIGO detector uses laser beams traveling back and forth along perpendicular arms several kilometers long. Under normal conditions, the beams are carefully arranged so that they cancel each other out when recombined. If a gravitational wave passes through the detector, it stretches space-time in one direction while compressing it in the other, altering the lengths of the arms by an almost imperceptible amount. This tiny mismatch produces a measurable signal, revealing the passage of a gravitational wave. For years, LIGO operated without detecting anything. Upgrades were made, sensitivity was improved, and skepticism persisted. Critics questioned whether the experiment would ever succeed, pointing out that the predicted signals were unimaginably small. Yet the researchers pressed on, refining their instruments and waiting for the universe to speak. That moment arrived on September 14, 2015, at 9:50 a.m. Eastern Time. Just 2 days after LIGO's newly upgraded detectors had been switched on in test mode, an unmistakable signal appeared in the data. It lasted only a fraction of a second, a brief chirp rising in frequency before abruptly cutting off. The signal was so clear and so strong that many researchers initially assumed it must be an internal test or calibration signal. No one claimed responsibility. As the realization set in, excitement turned to disbelief. The signal matched, almost perfectly, the predicted signature of two massive black holes spiraling toward each other and merging. According to the data, the black holes each had masses more than 30 times that of the Sun. They had collided more than 1 billion years ago, in a distant corner of the universe, releasing an immense burst of energy. In that final fraction of a second, the merging black holes converted a portion of their mass directly into gravitational waves. The energy released in this process amounted to nearly 10 to the 48th joules, briefly outshining every star in the observable universe combined. These waves then traveled across the cosmos at the speed of light, passing silently through galaxies, stars, and planets until they reached Earth. When they did, they altered the length of LIGO's arms by less than 1,000th of the diameter of a proton. And yet, that was enough. The detection was historic. For the first time, humanity had directly observed gravitational waves, confirming a major prediction of general relativity made a century earlier. Einstein had been right. Spacetime can ripple, and those ripples carry energy across the universe. Gravity was not an instantaneous influence, but a dynamic phenomenon capable of propagation. The implications extended far beyond a single detection. Gravitational waves provided direct evidence that gravity behaves like a field, similar in some respects to the electromagnetic field. Just as light and radio waves are ripples in the electromagnetic field, gravitational waves are ripples in the fabric of space-time itself. This placed gravity more firmly alongside the other fundamental interactions, while also highlighting its unique nature. One of the most profound consequences of this discovery was the realization that gravity has a finite speed. If the Sun were to suddenly disappear, the Earth would not immediately fly off into space. Instead, it would continue orbiting the region of space-time, shaped by the Sun, for about 8 minutes, until the gravitational disturbance reached it at the speed of light. This behavior aligned gravity with the relativistic universe, reinforcing the idea that no influence travels faster than light. The success of LIGO silenced many of its critics. In 2017, the experiment's founders were awarded the Nobel Prize in Physics for their achievement. By then, gravitational wave detections had become more frequent, each one offering new insights into extreme cosmic events that had previously been invisible. That same year, LIGO detected gravitational waves from a different kind of catastrophe: the collision of two neutron stars. Unlike black hole mergers, which emit no light, neutron star collisions produce electromagnetic radiation across the spectrum. In this case, the gravitational wave signal was followed by a burst of gamma rays and the appearance of a bright new point of light in the sky. For the first time, astronomers observed a single event using both gravitational waves and traditional telescopes. This moment marked the birth of multi-messenger astronomy. Gravitational waves provided information about the motion and mass of the merging objects, while light revealed details about the material ejected in the collision. Together, they offered a more complete picture of the event than either method could alone. Gravity had become a new sense with which to explore the universe. Beyond confirming Einstein's theory, gravitational waves changed how scientists think about observation itself. Light can be blocked, absorbed, or scattered by matter, limiting how far and how clearly we can see. Gravitational waves, by contrast, pass through almost everything unimpeded. They carry information from regions of the universe that are otherwise hidden, including the interiors of black hole mergers and the earliest moments after cosmic inflation. This new window on the universe also reshaped the discussion around gravity's nature. The existence of gravitational waves confirmed that gravity is not merely a static curvature, but a dynamic field capable of storing and transmitting energy. This brought gravity conceptually closer to the other fundamental forces, even as its underlying description remained geometric rather than quantum. At the same time, the weakness of gravitational waves underscored gravity's fundamental peculiarity. The waves detected by LIGO originated from some of the most violent events imaginable, yet their effects on Earth were astonishingly small. Only the most sensitive instruments ever built could detect them, and even then, only under ideal conditions. Gravity's weakness was once again on display, even in its most dramatic manifestations. This duality reinforced the central mystery of gravity. It can drive cataclysmic events that reshape the universe. Yet it interacts with matter so gently that its signals are almost lost in noise. Gravitational waves made this contradiction impossible to ignore. They showed gravity acting as a dynamic, propagating phenomenon, while simultaneously reminding us of its extreme subtlety. Perhaps most intriguingly, gravitational waves offered a glimpse of gravity's role in the universe's earliest moments. If violent cosmic events today produce detectable ripples in spacetime, then the birth of the universe itself should have generated a background of gravitational waves. These primordial ripples would carry information from times and conditions inaccessible to light, potentially revealing how gravity behaved at the very beginning. LIGO, however, was never designed to detect such ancient signals. Its sensitivity is tuned to relatively high-frequency waves produced by stellar-scale events like black hole and neutron star mergers. To explore gravity's role in the early universe, a new generation of instruments would be required, capable of detecting much longer wavelength distortions in space-time. The success of LIGO demonstrated that such ambitions were no longer unrealistic. What once seemed impossible had become reality, and the detection of gravitational waves transformed gravity from a theoretical abstraction into an observable phenomenon. Space-time itself had become a messenger, carrying stories from across the universe. Yet, for all that gravitational waves revealed, they did not resolve the deepest questions about gravity. They confirmed how gravity behaves, not why it exists or why it is so weak. They strengthened general relativity without reconciling it with quantum mechanics. Gravity remained both illuminated and mysterious, clearer in form, yet elusive in origin. As physicists celebrated the triumph of gravitational wave astronomy, they also recognized its limitations. The waves detected so far came from relatively recent cosmic events, not from the universe's earliest moments. To push further back in time, to probe gravity at its birth, new tools and new ideas would be necessary. The story of gravity was entering a new phase. Detection had replaced speculation, and observation had caught up with theory. But the ultimate goal remained unchanged: to understand where gravity comes from and why it behaves the way it does. To pursue that goal, scientists would have to listen not just to the loud, dramatic signals of merging black holes, but to the faint, persistent echoes left over from the universe's creation. Those echoes, if they exist, may hold the key to gravity's deepest secrets. And it is toward those earliest moments that the journey now turns. The discovery of gravitational waves forced physicists to rethink one of the oldest assumptions about gravity. For centuries, gravity had been treated as an influence that acted instantaneously, reaching across space without delay. This view was implicit in Newton's equations, where changes in mass or position were felt immediately, no matter the distance. But the detection of space-time ripples traveling at the speed of light made it clear that gravity does not behave this way. It does not issue commands across the universe in an instant. It communicates through propagation. This realization reshaped gravity's place among the fundamental interactions. If gravitational effects travel as waves, then gravity must be something that exists everywhere. Even in the absence of massive objects, waves require a medium of some kind, not a physical substance, but a structure capable of oscillation and transmission. In the case of gravity, that structure is space-time itself. Gravity, then, is not merely a relationship between objects, but a property of the fabric in which those objects reside. This idea aligns gravity more closely with the other fundamental forces than Newton ever imagined. Electromagnetism, for example, is understood as a field that permeates all of space. Electric charges disturb this field, producing waves that travel outward at the speed of light. Light itself is nothing more than a ripple in the electromagnetic field. The fact that gravity also produces waves suggests that it too is a field, capable of storing and transmitting energy. Yet, the similarities only go so far. The electromagnetic field interacts strongly with matter, exchanging energy readily and producing dramatic effects even at small scales. Gravity's field, by contrast, interacts so weakly that its ripples can cross entire galaxies without being significantly absorbed or scattered. This difference in strength explains why gravitational waves are so difficult to detect. Even when they originate from the most violent events in the universe, the finite speed of gravity carries profound implications. It means that gravitational information takes time to travel, just like light or radio signals. If the sun were to suddenly vanish, the Earth would not immediately respond. For about 8 minutes, it would continue orbiting the region of spacetime shaped by the sun's mass, unaware that anything had changed. Only when the gravitational disturbance reached Earth would its motion begin to alter. This thought experiment highlights the intimate connection between gravity and spacetime geometry. The Earth does not orbit the sun because it is pulled by an invisible force acting across empty space. It follows a path through curved spacetime, responding to changes in that curvature as they propagate outward. Gravity's influence is not an instruction issued from the sun, but a feature of the spacetime environment through which Earth moves. Understanding gravity as a field also clarifies why it behaves so differently from our everyday intuition. Fields are inherently distributed. They do not belong to individual objects but exist throughout space. Objects influence fields, and fields influence objects, but no single object owns the interaction. This perspective makes gravity less like a push or pull and more like a condition of the universe itself. In this sense, gravity is always present, even in regions of space that appear empty. Spacetime does not need matter to exist, and the gravitational field persists whether or not massive objects are nearby. Matter merely distorts that field, creating patterns of curvature that guide motion. The field itself remains, waiting to be shaped. This view helps explain gravity's universality. Unlike electromagnetism, which depends on charge, gravity responds to all forms of mass and energy without exception. Anything that carries energy, momentum, or pressure contributes to space-time curvature. This universality is built into the structure of the gravitational field, not imposed as an additional rule. At the same time, viewing gravity as a field raises difficult questions. Fields in modern physics are typically described using quantum theory, where interactions are mediated by particles and fluctuations are discrete rather than continuous. The electromagnetic field has photons, the strong force has gluons. If gravity is a field, it seems natural to expect it to have a quantum description as well. And yet, gravity resists this expectation. While gravitational waves behave like classical waves, they do not fit neatly into the framework of quantum field theory. Attempts to describe gravity in the same way as other fields quickly run into mathematical difficulties. The equations produce infinities that cannot be easily removed, and predictions lose their meaning at very small scales. Gravity's field-like nature appears to be fundamentally different from that of other interactions. This tension reflects a deeper divide in modern physics. General relativity describes gravity as a smooth, continuous deformation of space-time, while quantum mechanics describes the world as inherently discrete and probabilistic. Both theories are extraordinarily successful within their domains, yet they speak very different languages. Gravity, sitting at the intersection of these domains, exposes their incompatibility. The existence of gravitational waves makes this conflict impossible to ignore. Waves imply excitations of a field, but the field in question is space-time itself. Quantizing spacetime would mean breaking the smooth fabric described by general relativity into discrete units, a process that challenges our basic notions of geometry and locality. Gravity, unlike other forces, seems to demand a rethinking of what a field actually is. Despite these difficulties, the field perspective offers critical insights. It explains why gravity's effects accumulate over large scales and why they are negligible at small ones. A weak field acting everywhere can dominate the universe when enough matter is involved, while remaining imperceptible in microscopic interactions. Gravity's weakness is not a flaw of the theory. It is a defining feature of how the field operates. This perspective also reframes the hierarchy problem introduced earlier. If gravity is a field that extends through all of space-time, its apparent weakness may reflect how that field is distributed rather than how strong it is intrinsically. The field may be diluted, spread thin across vast regions or dimensions, leaving only a faint imprint in the world we experience. Such ideas would have seemed absurd in Newton's time and speculative even in Einstein's. But the detection of gravitational waves changed the conversation. Gravity is no longer inferred solely from motion and curvature. It is observed directly as a dynamic entity. This observation legitimizes questions about the structure, extent, and origin of the gravitational field. Importantly, understanding gravity as a field also unifies past insights. Newton's discomfort with action at a distance, Nordstrom's attempt to reconcile gravity with relativity, and Einstein's geometric description all find a place within this framework. Gravity is neither a mysterious pull nor a simple force. It is a manifestation of the structure through which all motion occurs. Yet even this understanding stops short of answering the deepest questions. Knowing that gravity is a field tells us how it behaves and how it propagates, but not why it exists or why it is so much weaker than other interactions. The field perspective sharpens the mystery rather than dissolving it. It reveals gravity's rules while hinting at a deeper origin. To uncover that origin, physicists must look to regimes where gravity's field was not yet weak or diluted. They must consider times when space-time itself was violently dynamic, when the universe was young and the familiar distinctions between forces may not have applied. In such conditions, gravity's field may have behaved very differently from how it does today. Gravitational waves provide a clue to this possibility. If space-time can ripple in response to black hole mergers, it should also have rippled during the universe's birth. Those primordial disturbances, if they still exist, would carry information from an era far beyond the reach of light. They would reveal gravity not as it is now, but as it was when space-time itself was being formed. The idea that gravity's field might preserve a memory of the universe's earliest moments is both tantalizing and unsettling. It suggests that gravity is not merely a force acting within the universe, but a record of how the universe came into being. To read that record, physicists must learn to listen to the faintest possible signals, buried beneath the noise of cosmic history. This realization shifts the focus once again. Gravity is no longer just a participant in cosmic events. It becomes a messenger from the past. Its waves carry stories not only of black holes and neutron stars, but of inflation, expansion, and the birth of space-time itself. To understand where gravity comes from, physicists are eventually forced to confront the universe at its very beginning. The cosmos we observe today is vast, structured, and relatively calm compared to its earliest moments. Galaxies drift apart, stars live out predictable life cycles, and space-time evolves slowly over billions of years. But none of this reflects the conditions under which gravity itself may have first emerged. According to the most widely accepted models, the early universe was nothing like the one we inhabit now. In its first fraction of a second, space itself underwent an extraordinary transformation. Rather than expanding gradually, the universe experienced a brief but violent episode of accelerated expansion known as inflation. During this period, space grew at an exponential rate, stretching microscopic regions to cosmic scales in an unimaginably short time. Inflation was not merely an increase in size, it fundamentally reshaped the universe. Any initial irregularities were smoothed out, leaving space remarkably uniform on large scales. At the same time, tiny quantum fluctuations were magnified, seeding the structures that would later become galaxies and clusters of galaxies. The universe emerged from inflation vast, cold, and nearly empty. Its energy spread thinly across an enormous volume. Yet this state could not persist. A universe devoid of particles, radiation, and matter bears little resemblance to the one we observe today. To bridge this gap, cosmologists propose a phase known as reheating. During reheating, whatever field or mechanism drove inflation decayed, releasing its stored energy into particles and radiation. This event effectively repopulated the universe, filling it with the ingredients necessary for stars, planets, and life to eventually form. In many models, this reheating phase is considered the true beginning of the hot Big Bang. It marks the moment when the universe transitioned from a cold, rapidly expanding vacuum into a dense, energetic plasma. Temperatures soared, particles collided incessantly, and the familiar forces of nature began to take on their modern forms. Gravity, if it already existed, would have operated under conditions far removed from those we experience today. Crucially, inflation and reheating would not have occurred quietly. These processes involved enormous energies and rapid changes in the structure of space-time. According to general relativity, such dramatic events should have generated gravitational waves, unlike the waves detected by LIGO, which come from relatively recent astrophysical events. These waves would have been produced at the dawn of the universe itself. These primordial gravitational waves would be extraordinarily faint by now, stretched and diluted by billions of years of cosmic expansion. Yet, if they exist, they would still be passing through us today, carrying information from a time far earlier than any light we can observe. Light cannot reach us from the first moments of the universe because the early cosmos was opaque, filled with charged particles that scattered radiation relentlessly. Gravitational waves, by contrast, travel freely through such conditions. This makes them unique messengers. While telescopes allow us to see back to around 380,000 years after the Big Bang, gravitational waves could, in principle, provide information from fractions of a second after the universe began. They offer a direct probe of inflation, reheating, and the behavior of gravity under extreme conditions. In this sense, gravity becomes not just a force, but a historical record. The precise nature of these primordial waves depends on the details of inflation itself. Different models predict different patterns of gravitational radiation, varying in strength, frequency, and distribution. Some scenarios involve a rapid, violent reheating process, producing strong bursts of gravitational waves. Others involve a slower, more gradual transition, leaving a subtler imprint on space-time. Detecting these differences would allow physicists to reconstruct events that occurred when the universe was less than a second old. It would provide experimental access to an era otherwise hidden from observation. In effect, gravitational waves could allow us to listen to the universe's first moments, rather than merely infer them from later consequences. Unfortunately, the instruments currently in operation are not sensitive to these ancient signals. LIGO and similar detectors are tuned to frequencies associated with stellar mass objects like black holes and neutron stars. The primordial waves from inflation would be far longer in wavelength, stretching across millions of kilometers or more. To detect them, a very different kind of observatory is required. This is where future missions come into focus. Projects such as the Laser Interferometer Space Antenna, or LISA, are designed to operate in space, far from terrestrial noise and interference. With arms millions of kilometers long, such instruments would be sensitive to low-frequency gravitational waves inaccessible from Earth. They represent humanity's attempt to extend its hearing deeper into the gravitational spectrum. If successful, these observatories could separate the steady background of primordial gravitational waves from the cacophony of signals produced by stars and black holes. This would be a remarkable achievement, akin to hearing the faint hum of the universe beneath the noise of its ongoing activity. It would allow physicists to test theories of inflation and early universe physics with unprecedented precision. The implications for gravity are profound. Detecting primordial gravitational waves would confirm that gravity was already active during inflation, shaping and responding to the universe's earliest dynamics. It would demonstrate that the gravitational field is intrinsic to space-time itself, not something that emerged later alongside matter. Gravity would be shown to predate stars, atoms, and perhaps even mass itself. This possibility raises subtle questions. If gravity existed before particles acquired mass, then its origin cannot depend solely on mechanisms like the Higgs field. Instead, gravity must be tied to energy, momentum, and the structure of space-time in a more fundamental way. Its weakness in the modern universe would then reflect how those early conditions evolved, not a simple property of matter. At the same time, primordial gravitational waves could reveal how gravity behaved when space-time curvature was extreme. General relativity describes gravity well under many conditions, but it may not be complete at the energies present during inflation. Deviations from predicted wave patterns could signal new physics, pointing toward a deeper theory that unifies gravity with quantum mechanics. This is why inflationary gravitational waves occupy such a central place in modern cosmology. They offer a rare opportunity to test ideas about gravity's origin experimentally, rather than relying solely on mathematical consistency. In a field where speculation often outpaces observation, such data would be invaluable. The search for these waves also highlights gravity's dual role as both actor and witness. Gravity shaped the expansion of the universe, influenced the distribution of matter, and guided the formation of structure. At the same time, its waves recorded those events, preserving information that may still be accessible today. Few forces play such a dual role. Yet even this optimistic picture comes with uncertainty. Inflation itself, while widely accepted, remains a theoretical framework rather than a directly observed phenomenon. Reheating is inferred rather than measured. The gravitational waves predicted by these models have not yet been detected. Each step in the argument depends on assumptions that must ultimately be tested. Still, the logic is compelling. If gravity behaves as a field capable of propagation, and if the early universe underwent violent changes, then gravitational waves are an inevitable consequence. Their absence would be as informative as their detection, forcing a re-evaluation of current models. Either outcome would deepen our understanding of gravity's role in cosmic history. In this way, the question of gravity's origin becomes inseparable from the question of the universe's birth. To understand why gravity is weak today, we may need to understand how space-time itself came into being. The universe's earliest moments hold the key, encoded not in light, but in the subtle trembling of space-time. As physicists continue to refine their instruments and theories, they are listening ever more carefully for these primordial echoes. The hope is that one day, the universe will reveal its earliest secrets through gravity alone. When it does, gravity may finally tell us not just how it acts, but where it truly comes from. And yet, even if those echoes are detected, another puzzle remains: gravity's relationship to mass, long assumed to be fundamental, may not be as straightforward as it seems. To explore that tension, we must turn to a different discovery, one that reshaped our understanding of mass itself. That is where the story goes next. For much of scientific history, gravity and mass were treated as inseparable. It seemed obvious that objects fall because they have weight, and weight comes from mass. Newton's equations reinforce this intuition, describing gravity as an attraction between masses that grows stronger as those masses increase. For centuries, this view worked well enough that few felt the need to question it. Modern physics, however, has complicated this picture. In 2012, experiments at the Large Hadron Collider confirmed the existence of the Higgs boson, a particle associated with the Higgs field. This field is responsible for giving mass to many fundamental particles, allowing matter to have weight and structure. The discovery clarified where mass comes from, but it also raised an unexpected question about gravity's role in the early universe. According to current cosmological models, the Higgs field did not exist during the earliest moments after inflation. Mass, as we experience it today, emerged only later as the universe cooled and underwent a series of phase transitions. If gravity depended directly on mass, then it should not have existed in any meaningful way before this point. And yet, inflationary models and general relativity both suggest that gravity was already shaping spacetime long before particles acquired mass. This apparent contradiction reveals a subtle but crucial distinction. In Einstein's theory, gravity does not respond to mass alone. Instead, it responds to energy, momentum, and pressure, all of which are combined in what physicists call the stress-energy tensor. Mass is only one form of energy, and not the most fundamental one. Even massless entities can influence and respond to gravity. Light provides the clearest example. Photons have no rest mass, yet they are bent by gravity as they pass near massive objects. This bending is not a side effect or approximation. It is a direct prediction of general relativity. Light follows the curvature of space-time, just as matter does, demonstrating that gravity is not tied exclusively to mass. This insight reshapes how we think about gravity's origin. If gravity acts on energy itself, then it does not require mass to exist. It can operate in a universe filled with radiation, fields, and extreme energies. Even before particles become massive, gravity, in this sense, is more fundamental than mass, not less. The separation of gravity and mass helps explain why gravity could emerge during the Planck epoch, or inflationary era. Space-time could curve and evolve in response to enormous energy densities. Even in the absence of familiar matter, the later appearance of mass through the Higgs field changed how gravity manifested, but not the underlying principle that space-time responds to energy. This realization also deepens the mystery of gravity's weakness. If gravity is not anchored to mass alone, then its feeble strength cannot be explained simply by how heavy particles are. The explanation must lie elsewhere, perhaps in how gravity couples to energy, or in how space-time itself is structured at the most fundamental level. By disentangling gravity from mass, physicists gained clarity, but not closure. Gravity remains universal, acting on everything, yet strangely subdued compared to other interactions. Understanding why requires pushing beyond the emergence of mass and into regimes where space-time and quantum physics collide. That collision is unavoidable. To truly explain gravity's origin, physicists must confront the deepest incompatibility in modern science: the tension between general relativity and quantum mechanics. And it is there, at the smallest possible scales, that the story now turns. To reach the origin of gravity, physics is forced into its most uncomfortable territory. This is the domain where general relativity and quantum mechanics must both apply, yet refuse to cooperate. Each theory is extraordinarily successful within its own regime, but when combined, they produce contradictions that cannot be ignored. Gravity sits precisely at this fault line, exposing the limits of our deepest understanding. The conflict becomes unavoidable at the smallest possible scales, during what is known as the Planck epoch. This period occurred when the universe was less than a fraction of a second old and compressed into a region unimaginably small. At this scale, space-time curvature becomes extreme, and quantum fluctuations dominate all behavior. The smooth geometry assumed by general relativity breaks down, while quantum theory lacks a way to describe space-time itself. In quantum physics, forces are typically explained through quantization. Fields are broken into discrete packets, and interactions are mediated by particles. Electromagnetism has photons, the strong force has gluons, and the weak force has W and Z bosons. By analogy, gravity is expected to have its own quantum messenger, a hypothetical particle known as the graviton. The problem is that gravitons have never been detected, and may never be. Gravity is so weak that detecting a single graviton would require an experiment larger than the solar system. Even worse, when physicists try to build a quantum theory of gravity using standard methods, the mathematics spirals out of control. Calculations produce infinite results that cannot be tamed or corrected. Physicists describe this failure by saying gravity is non-renormalizable. In simpler terms, the theory cannot be repaired by adjusting a finite number of parameters. When space-time itself is treated as a quantum object, its own energy becomes a source of further gravity, which creates more energy, more curvature, and more divergence. The equations feed back on themselves endlessly. This breakdown suggests that gravity cannot be quantized in the same way as other forces. Either space-time is not fundamental, or our approach to quantization is incomplete. Gravity may not be a force added on top of space-time, but a manifestation of space-time's microscopic structure itself. If so, trying to describe it with traditional quantum fields may be fundamentally misguided. In response to this impasse, physicists have explored alternative frameworks. One such approach is loop quantum gravity, which treats space-time as built from tiny, discrete loops woven into a fine network. In this picture, space is not smooth but granular, and gravity emerges from the connectivity of these loops. Curvature becomes a property of how the network is arranged, not a continuous deformation. Another approach, even more radical, is string theory. Here, the fundamental building blocks of reality are not particles, but tiny vibrating strings. Different vibrations correspond to different particles, including one that naturally behaves like a graviton. Gravity emerges automatically, but only if the universe has more dimensions than the four we experience. Both approaches attempt to resolve the same problem from different angles. They accept that gravity's incompatibility with quantum mechanics is not a technical glitch, but a sign that something deeper is missing. Space, time, and gravity may not be fundamental ingredients, but emergent features of a deeper reality. What unites these ideas is a growing suspicion that gravity's weakness is not accidental. It may reflect how gravity emerges from underlying structures rather than how strong it truly is. To explore that possibility, physicists must be willing to abandon the assumption that our universe is limited to the dimensions we perceive. That leap leads directly to the most daring idea yet, that gravity's true home may lie beyond our visible universe, leaking into our reality from elsewhere. As physicists grappled with gravity's refusal to fit into quantum theory, a growing number began to question an assumption so basic it was rarely stated aloud. Perhaps the universe we experience is not the whole stage on which reality unfolds. Perhaps the weakness of gravity is not a flaw in our equations, but a clue that gravity is reaching us from somewhere beyond our familiar dimensions. String theory had already suggested this possibility. In order for its mathematics to remain consistent, reality must contain more dimensions than the three of space and one of time that we perceive. Traditionally, these extra dimensions were assumed to be curled up at unimaginably small scales, hidden from observation. Gravity, however, seemed to offer another possibility, one that did not require dimensions to be microscopic. This is where the work of physicist Lisa Randall enters the story. In the early 2000s, Randall and her collaborator Raman Sundram proposed a radically different picture of the universe. In their model, our entire observable universe exists on a three-dimensional surface embedded within a higher dimensional space. These surfaces are known as branes, derived from the idea of membranes. In this picture, all the familiar forces of nature, electromagnetism, the strong force, and the weak force, are confined to our brain. They cannot escape into the higher dimensional space beyond it. Gravity, however, behaves differently. It is not bound to our brain in the same way and can spread into the surrounding higher dimensional bulk. If gravity is free to move through extra dimensions, its apparent weakness becomes easier to understand. From our perspective, only a fraction of gravity's true influence leaks back onto our brain. The rest disperses into dimensions we cannot access or observe directly. Gravity is not weak by nature, it is diluted by geometry. The Randall-Sundram model takes this idea even further by introducing warped geometry. Instead of extra dimensions being flat and uniform, they are curved in such a way that gravity becomes concentrated near a separate brane, sometimes called the gravibrane. The further one moves from this gravibrane, the weaker gravity becomes, dropping off exponentially. In this scenario, our universe happens to sit at a distance from gravity's primary source. We feel only the faint residue of its full strength, while other forces remain unaffected because they are trapped on our brain. The hierarchy problem, once a baffling numerical coincidence, emerges naturally from the geometry of higher dimensional space. This framework also offers a possible explanation for why gravitons have never been detected. If gravity's quantum particles are free to wander into extra dimensions, the probability of one interacting with detectors in our universe would be extraordinarily small. Their apparent elusiveness would not reflect their absence, but their freedom. What makes this idea especially compelling is that it does not require gravity to be fundamentally different in strength from other forces. Instead, it suggests that our measurements are incomplete because we are observing only a projection of a higher dimensional reality. Gravity's weakness becomes a matter of perspective rather than principle. Of course, such ideas are controversial. Extra dimensions have never been observed directly, and brain world models remain speculative. Yet they are mathematically consistent and offer concrete predictions that could, in principle, be tested. Deviations from Newtonian gravity at very small distances or signatures in high-energy particle experiments could provide evidence for their validity. What these theories share is a willingness to rethink the boundaries of reality itself. Rather than forcing gravity to conform to our existing frameworks, they expand the framework to accommodate gravity's strange behavior. In doing so, they turn gravity's weakness from a problem into a guide. If gravity truly belongs partly elsewhere, then understanding it fully may require looking beyond our universe rather than deeper within it. The answers may lie not in smaller particles or higher energies, but in dimensions we have yet to perceive. And yet, even this bold reimagining does not bring the journey to a definitive end. Mathematics alone is not enough. As history has shown, gravity's story only advances when theory meets observation. The final word will belong not to equations, but to evidence. And so, the question remains open, balanced between imagination and measurement, waiting for the next discovery to tip the scale. After centuries of study, gravity remains both familiar and elusive. We have learned to measure it with extraordinary precision, to predict its effects across the cosmos. and even to listen to its faint vibrations as space-time itself ripples. Gravity guides planets, shapes galaxies, and governs the evolution of the universe on the largest scales imaginable. And yet, for all this knowledge, its true nature continues to slip through our grasp. This journey has revealed a recurring pattern. Each time physics believed gravity was understood, deeper questions emerged. Newton described its behavior but doubted its essence. Einstein redefined it as geometry, only to leave its origin unexplained. Modern discoveries have confirmed gravity's predictions while simultaneously exposing its isolation from the rest of fundamental physics. The detection of gravitational waves stands as a powerful reminder of this pattern. For decades, they were dismissed as mathematical artifacts or experimental impossibilities. Then, in a brief fraction of a second, space-time itself proved otherwise. What once seemed beyond reach became observable, reshaping not only our understanding of gravity, but how we explore the universe. Today, gravity occupies a strange position. It is the weakest of the fundamental interactions, yet it controls the largest structures in existence. It behaves like a field, yet resists quantization. It acts universally, yet may not belong entirely to our universe at all. Each of these contradictions hints that gravity is not simply another force, but something more fundamental and more subtle. Theories of extra dimensions, quantum spacetime, and emergent gravity may or may not reflect reality. Many will likely be revised or discarded, just as earlier ideas were. But history suggests that progress comes not from clinging to certainty, but from questioning assumptions that once seemed unbreakable. Gravity has repeatedly forced physicists to rethink space, time, and reality itself. What remains clear is that gravity is not finished teaching us. New instruments, new observations, and new ideas will continue to test the boundaries of what we think is possible. The faint echoes from the universe's earliest moments may yet reveal how gravity was born. The behavior of space-time at extreme energies may uncover connections we cannot yet imagine. In the end, gravity's weakness may be its greatest strength. Because it is so subtle, it preserves information across cosmic time. Because it interacts so gently, it carries messages from places light cannot reach. Gravity does not announce itself loudly, but it endures, quietly shaping everything that exists. And perhaps that is fitting. A force so soft, so patient, and so persistent may never yield its secrets all at once. Understanding gravity may require not a single breakthrough, but a long conversation between theory and observation, stretching across generations. For now, gravity remains what it has always been, a quiet force behind the universe's greatest power, waiting for us to listen more closely. And so, this journey comes to a quiet pause. We have followed gravity across scales both vast and intimate, from the ground beneath us to the deepest reaches of space. What we have uncovered is not a final answer, but a clearer sense of how much remains unknown. Gravity continues to shape the universe in silence, revealing just enough to invite curiosity, but never enough to end the story. For now, we step back, leaving this mystery open. The cosmos is patient, and so is discovery. When the next journey begins, we will return, ready to listen, to question, and to explore once more.